When you make an application, there's a lot of different reasons you would want to store and read data from your computer. It often gives you a lot more power to perform a task depending on the goals you're trying to accomplish. A program without file input-output capabilities would be limited to read data directly inputted from the user by their keyboard, which is bad if the data is complex like an image or if it's really large. And the more data you require or the bigger your program is, the more important it becomes to have an efficient way of reading and writing that data. This video will talk about the different ways of storing data and how we implemented one of those methods for our games Cryoclastic and Nebula Four. When you first make a program that requires data storage, the data file will probably end up looking something like this. You have some important variables at the top of the file, and the data itself is afterwards. Inside the program, you may hardcode into how the data should be read. Like maybe you say the first number is the state of the file, the next two are the number of enemies in the world, the next 5 describe how long to play a sound, and so on. But this approach isn't very versatile. If you adjust your program later on to require an additional variable at the top, you either need to change each of your data files to match this pattern, or you need to somehow adjust your program to detect which files are outdated and fix the format then while the program is running. Also, this file isn't very readable. It may make sense to the programmer, as long as they remember the pattern they set previously, but anyone else looking at the data wouldn't be able to change it easily. For instance, maybe this number in the middle controls the volume of the program. If you wanted to edit the volume through this data file, you wouldn't really be able to because it's so unorganized. This leads us to a slightly more orderly file next. This file is very similar to the previous example, but it includes text on some lines. A program would read it the same, but now it would ignore lines beginning with a pound symbol. This leads us to much higher readability, and we would quickly be able to identify certain variables like volume when we couldn't have before. Although, the biggest problem with this method of storage is still how simple it is. Storing anything more complicated than whole numbers or letters becomes a big problem. This leads us to more structured but flexible storage methods like Json. Json stands for JavaScript Object Notation, although it isn't strictly connected to JavaScript anymore. It provides a much more organized way of storing data than the previous methods, while also maximizing parsability. There are other storage methods similar to Json like XML and YAML, but Json is my personal favorite for its readability and relatively low storage requirements. The basic idea of Json is it allows the storage of data in key value pairs, as in you parse a JSON document for variables, and you're able to grab the values of specific variables based on a name. As such, if we need to change the volume of our program like in our previous examples, we would now just locate the text area in our file named volume and adjust the number next to it. This may look identical to our previous method, but it actually leads to a lot more flexibility in our code. In our last example, we would have needed to design our program to specifically read a certain amount of numbers from the entire file, or maybe an amount of numbers from each line. This means a 50-second number in our file would have had to have represented the volume of our program. But what happens if the user changes our file? If they deleted the first number of the file, then all the data after it would have been one number off, potentially having catastrophic effects for our program, and maybe even rendering the entire file useless as a result. One solution to this problem would be to ignore it and say anything the user changes is their own fault. But with a storage method like Json, this isn't necessarily an issue. Now, users can identify areas they may want to change and can probably piece together what certain sections mean, which gives them a lot more control over the data. The programmer can even identify areas where the data was misinputted somehow. Now, if they want to set the volume of the program, they need to locate the volume key. If the key isn't found, they give it a default value. If the key is found, but it's garbled text instead of a number, they can give it a default value again. It's become significantly harder to break our program now as long as we're careful when designing the program to avoid breakage. And with a format as flexible as Json, we can store data a lot more creatively than the linear methods shown before, now with containers, nested lists, and references all being possible. Now that we've chosen a method to store our data, the next problem is deciding how to turn information from our program into text in a file. The first issue lies with a concept called data serialization. Serialization involves the process of converting an object into a stream of text, and then turning that text into an exact copy of the original object. This sounds simple enough, but it turns out to be a lot tougher when you have a lot of objects referencing each other in a program. Consider this simple example. We want to save a person to a file where a person consists of a first name, an age, and a height. This is pretty easy with the help of Json. We can just make the keys of the variables be the words first name, age, and height, and the values be whatever those things are set to. Now, let's pretend a person also consists of their parent. How would we store the person now? Computer programs will solve this problem by having a reference to the object be stored instead of the object itself. That basically means this person consists of now a first name, age, height, and a location in memory to another person. The problem with this approach is that memory locations cannot be reconstructed at another point in time. If we stored this data in a text file and recreated it a few minutes later, there's no guarantee that parent is located at the same place in memory. Another approach to solving this problem would be to store the data of the parent in that slot directly, like this. But it creates two new problems. If we changed parent to become sibling and two siblings link to each other, how will we be able to store that object? A person will link to a sibling, and then the sibling will link back to the same person, and now we have to keep storing ourselves again and again until our computer breaks. The other option is more of a semantic one. Let's assume there aren't any repeated sections like before. If we consider this current person to be the base object where we begin, then the parent is stored only once beneath the base. In this situation, we're left to believe the parent is now less important than the base object, since it's stored underneath the base. What if the parent is actually integral to the program though, and we chose the base arbitrarily? Maybe the parent is a famous actor, and the program is meant to categorize movies. In which case, we'd probably care a lot more about that actor than their child, and our data storage method should reflect this. Unfortunately, there's no single best way of serializing data, and it's something that takes a lot of organization to get right, but Json provides some pretty neat tricks to help out. One solution to the previous example is to keep every person in the program at the same level, and have each person store a unique ID to identify them. Then, when we want to say person A is the parent of person B, we store that ID in the parent slot instead of a physical memory address. When we load the data into memory, all we do now is read the data from the file and create the people first, then link up each person by their IDs afterwards. Now that we've settled on using Json as our storage format, and we've decided on how we're organizing the data to comply with serialization standards, our next step is to read the text from the file into our program. This is actually a harder problem than it sounds when you consider the fact a program doesn't really think in terms of words and formatted strings. It's much more comfortable thinking on a character-by-character basis. So how do we read a JSON file and extract the information from it? And how do we apply this program to extract information from every possible JSON file so we're prepared if our program becomes bigger in the future? And how do we recognize when a file is broken or formatted incorrectly and recover swiftly instead of crashing our program? Let's break the problem into simpler steps to make it easier for us. A computer is best at interpreting a text file as a list of characters, but for our purposes, we need to interpret our JSON file as a collection of key value pairs. Although we can easily group these configurations of characters together as long as we know what we're looking for. Let's consider a grouping of characters to be a lexeme and a description of a lexeme to be a token. If we look at an English sentence like, "they drive a fast car," we can break the sentence into a group of lexemes and identify those lexemes as tokens, which now becomes pronoun, verb, article, adjective, noun, punctuation. Now, looking at the list of tokens, we can rigidly define whether or not the sentence is valid, or a proper English sentence. We can look at an English textbook and see that the subject of the sentence is the pronoun, and they are performing a verb on the object of the sentence, which is the noun. We can also notice how the lexeme of the first token begins with a capital letter, and how the sentence ends with a punctuation token. As a result of these rules and possibly many others, we can conclude that this sentence is proper English. The same process can be used on a JSON file, because we can properly define the grammar of what the JSON is supposed to match. These are the rules of the JSON format. It looks a little tough to read, but let's walk through it. Grammars like this one describe the patterns tokens must follow, and they're essential to create things like programming languages or data protocols. Grammars are made up of terminals and non-terminals, where terminals are easily definable, rigid collections of tokens, and non-terminals are things that are made up of a lot of other terminals or non-terminals. In other words, terminals end, non-terminals don't. You can notice that in this grammar, non-terminals begin with a capital letter and are defined on a new line, and terminals begin with a lowercase level and should be self-evident, or really easily defined by a programming language. Finally, grammars usually have special characters like parentheses or square brackets, but if those characters are needed in our language for whatever reason, then the needed characters are underlined, like we'll see later with lists. Anyways, we start at the first line of the grammar, which in this case tells us that JSON is equal to a dictionary being something that we'll define next. A dictionary is now equal to an opening curly bracket, some stuff in the middle, and a closing curly bracket. The parentheses here tell us that the stuff between them are completely optional. We don't actually need to have strings or values here to be considered a valid JSON file. As such, we can create a valid JSON file by just typing 2 curly brackets, which is completely fine given this grammar. Anyways, a dictionary can optionally contain a string of letters, surrounded by quotation mark, a colon, and a value in that order. The brackets here tell us that we can optionally have a repeated section of things next. In this case, a comma-separated repeat of strings and values. A value is equal to potentially a lot of different things. It can be a string, again surrounded by quotation marks, an integer, a float, a boolean, as well as another dictionary or a list. When we put these vertical lines here, that means that only one of them can be used where we see the word value. Additionally, a list follows a very similar format as a dictionary does. It must begin and end with square brackets, it can optionally have a single value, and it can optionally repeat commas and values forever. And there we have it. Any input text in the world that matches this format is considered valid JSON, and as such, we should be able to parse information from it. Here's a real example of a JSON file which matches this format. This file specifically is actually one from our game Cryoclastic, and it stores information on the options the player can change from menus. At the moment, there are 2 menus the player can change, video and audio. The video screen is represented as a dictionary of 4 key value pairs, being quality, shadows, lighting, and vsync. The audio screen is a similar situation, now with numbers instead of words being stored. The idea is, now that we have a text file full of information, we step through character by character forming tokens and see if those tokens match up to the grammar we defined earlier. The file begins with a curly brace, which is required in a dictionary so we can proceed easily. Then we notice how there's a new line character here and a bunch of spaces. In our implementation of a JSON parser, we're able to ignore these whitespace characters since they're not very important to our grammar. The next important character read is a quotation mark, which tells us there's data inside of this dictionary as the character read isn't a closing bracket. We read this block of characters until we see another quotation mark and set the token to string, and the lexeme to video. Then we see a colon and another opening curly bracket. There's only one value type which can contain a curly bracket as the first character, and that's another dictionary. At this point, we continue parsing these characters token by token like we have, pattern matching what we're able, and we keep going until there's either something that doesn't match with our grammar or we reach the end of the file. And now, if we successfully make it to the end, we can send that data off to somewhere else in the program and close our file for us to continue doing something else. And that's basically it for the JSON parser. As long as we design it good enough to detect errors in input files and attempt to recover, we can use this parsing script anywhere we require the use of data storage. In Cryoclastic, we utilize our JSON parser for both the options menu and also the player save state. The save data contains a lot more information, including the name of each AI, whether or not the AI is active, the player's position and rotation, and what weapons the player has equipped in their current status. Our system of interpreting tokens and placing the information in data structures ourselves is super versatile too. We can quickly save and load data at the press of a button near instantly. We're using the same parser in the development of Nebula 4 to save information on the completed missions a player did, and even save the data the program needs to run waves and spawn enemies in missions. We'll be showing off the game in action a lot in the future, so be sure to subscribe to see our videos when they come out. Finally, we have a Twitter to share smaller bite-sized images and clips of gameplay and development news, so follow us there to get updates too. See you all next time.